Hello, everybody. This is 9.3 continuity. Okay, so today we will go over 3 rules that define continuity of a function at a certain given value of x, right? So the 3 rules of continuity. The very first rule is the limit must exist. So number 1 says, oops. Number 1 says the limit as x approaches c must exist. All right, if we pass that rule, then rule 2 says the point must exist. F at c exists. And then the third rule says if we pass rule 1 and we pass rule 2, the third rule says the limit value must equal the point value. So what does that mean is the y value of the limit must equal the y value of the given point. And if you pass all 3 of these rules, then you are considered fully continuous at x equals some value c. Okay, but today we want to prove why things are discontinuous by using these 3 rules of continuity. The reason we prove why something's discontinuous is because it's just way too easy to be continuous, let me tell you. So why not use these rules in another way to prove discontinuity at a certain x value? All right, and trust me, it's just way more fun that way. Okay, so we must pass all 3 rules in order to be considered fully continuous. If you fail one rule, doesn't matter what it is, it's thrown out and the function's considered discontinuous. Okay. All right. So we'll start with our first example. This one says, use the definition of continuity to discuss the continuity of this function at the x value of 1. Or when x equals 1, what is the continuity of this function? And we will use the 3 rules, right? Okay, the first rule is, does the limit exist? Well, let's look at 1. Okay, so at 1, or when x is 1, to be more appropriate, we see that we have 2 different y values. Okay, so the very first question says, what is the limit as x approaches 1 from the left? What is the limit as x approaches 1 from the left? So as we approach 1 from the left side, again, we want to know what are our y values doing. So as we approach 1 from the left, we see that we come to this graph, we have to jump up to this graph, and we are tracing along as x gets closer and closer and closer to 1. And we see that as x gets closer and closer to 1, y starts to get closer and closer and closer to 4. So what we say is the limit as x approaches 1 from the left will be 4. All right. And once again, we can run it back. Just go over it, touch on it one more time. So, oh, my hair is crazy, sorry. No haircut till next August. That's when we come back to campus. Pending miracle vaccine. All right. All right. Can't wait for the kids in spring to watch these videos, you know? Okay. So, once again, as we approach 1 from the left side, my y values get closer and closer and closer to 4. So, the limit from the left at 1 is going to be 4. All right, look at the next one. what is the limit as x approaches 1 from the right? So back to the graph. As we approach 1 from the right side, so as x gets closer to 1 from the right, we see that my y values get closer and closer and closer to 1. So once again, run it back. As x gets closer and closer and closer to 1 from the right side, y gets closer and closer and closer to 1. All right, so this means that the limit from the right is 1. Okay, excellent. So now this goes with our third question. What is the limit as x approaches both sides at 1 of f of x? Well, remember, this is the theorem, the existence of a limit. The limit from the left is 4. The limit from the right is 1. In order for a limit to exist at x equals 1, the limits must be equal. The left hand and the right hand limits must be equal. Does 4 equal 1 or does 1 equal 4? And that answer is no. So since these are not equal, this means that the limit at 1 does not exist. Okay, which means if we're looking at rules of continuity, the first rule says that the limit must exist. So since the limit does not exist at 1 from both sides, this would fail rule 1, making it discontinuous at 1. Okay. So, and we'll put that on E when we get there. D says, find the function value f of 1. So remember what this means. This says, when x is exactly 1, what is the value of y? When x is 1, what is the value of y? That's what that means. So let's go back, read the graph. So when x is exactly 1, we have two values. We have 1 and we have 4. Well, which point do you choose? And I mentioned it last time in the last notes, is that a defined point overrules an undefined point. So since 1 is undefined and 4 is defined, this means that f of 1 is going to be 4. We always, always, always state the defined point. That would be the same thing if we did it here. If I said, what is f of 3? Do you state this point or that point? Do you state the defined point or the undefined point? And we would state the defined point. So f of 3 would be 1. So that's what we're doing here. So with that being said, f of 1 is 4. Okay, but none of that matters is because if you look at the rules of continuity, 1, the limit as x approaches 1 must exist, which we already failed. 2, the point must exist, which is good. We got that the point existed at 4. When x is 1, y is 4. But again, it does not matter because we failed rule 1. Therefore, this function at x equals 1 is discontinuous. All right. I guess I could have stated all that down there. Let's see. Is f continuous at x equals 1? And we're going to say no. F is discontinuous at x equals 1 because the limit does not exist. Because the limit as x approaches 1 of f of x does not exist. There you go. And again, since we are referencing rules of continuity, let's just look at them again. We failed rule 1. And since we failed rule 1, this makes it discontinuous at x equals 1. If one or more of the 3 conditions fails, then it is discontinuous. And that is how we use the rules of continuity to prove that something is discontinuous. Okay, fun times, right? Okay, next are continuity properties, which are basically domain properties. So if you know the domain of a function, you know the continuity of that function. You know where that function exists. So let's go over some functions really fast. So in the theorem, in the properties, A says a constant function, f of x equals k, where k is a constant, is continuous for all values of x. So what does it mean to be a constant function? Well, what's up here, right? If I said f of x equaled 5, this is the same as me saying y equals 5. Now, think of the graph. Y equals 5 is what type of line? Don't say straight. All lines are straight. Y equals 5 is a horizontal line that goes on infinitely, right? Y equals 5 looks like this, where that tail goes to negative infinity, that tail goes to infinity, and therefore the domain of any constant function is all real numbers. So what we can say for a constant function is that it is continuous from negative infinity to infinity. And now you see why I say it's way too easy to be continuous. Look at that. A horizontal line will pass all 3 rules of continuity. There's no fun in that. Okay. B, for n, a positive integer, f of x equals x to the n is continuous for all x. Okay, well, what does it mean to be an integer? To be an integer means you are a whole number and you are a positive number. So an integer is a whole positive number from 1 to infinity. So that's what it means to be an integer, a whole positive number. Okay, so they're continuous for all x as well. So if I wrote some examples, So let's just say f of x equals x, or f of x equals x squared, f of x equals x cubed, or f of x equals x to the 100th. And no matter, and remember the power of that is 1, and no matter what the power, it does not matter. Since these are all, these exponents, these degrees are all whole positive integers, right? They're whole positive numbers. Their domain, no matter what, will be the same as a constant. Their domain will always be all real numbers, from negative infinity to infinity. Or in continuity terms, any power function with a positive exponent, a whole positive exponent, will be continuous from negative infinity to infinity. There you go. Okay. C, a polynomial function is also continuous for all x. All right. Well, now we're back to definitions. What does it mean to be a polynomial? To be a polynomial, it's the same rules as B. To be a polynomial, you must have variables that have positive integers as exponents. So essentially, B and C are the exact same thing. In B, all of those x's have positive exponents. They have integers, positive integers. To be a polynomial, all of your terms must have positive integer exponents as well. So for C, I could write, I don't have to write anything. Everything I wrote here, those are all polynomials. Doesn't matter. You could have a one-term polynomial, a two-term polynomial, a three-term polynomial. These are all polynomials. But let's just say I made up a polynomial. Let's say f of x equaled x to the 5th plus x to the 4th plus x. This is a polynomial function because all my exponents have whole positive numbers or positive integers. And no matter what type of polynomial I have, the domain for that will, guess what it's gonna be? Negative infinity to infinity. Now, they don't share the same graph. I'm just saying they share the same domain. All of these have different graphs. But I'm just telling you that these type of functions, these polynomial functions, will be continuous from negative infinity to infinity. So these functions have full continuity, which means they are not fun because we want functions that are discontinuous. Those functions have character. All right. Now we get into some good functions. D, a rational function is continuous for all x except those values that make a denominator 0. Okay, good. So when I say, I can start here. Sure. So when I say rational function, remember rational is just fancy for fraction. So let me make something up. Let's say r of x equaled 1 over x minus 3, right? 1 over x minus 3. Well, in order to find where this function's continuous, for its domain, you would have to take the denominator and set it equal to 0. This means that you would get x equals 3. But if x is 3, the denominator becomes 0. So we say that the domain is any number they want to be except 3, which means in interval notation, we would write negative infinity to 3 union 3 to infinity. Okay, so we would say in continuity terms that my rational function of 1 over x minus 3 is continuous everywhere except at 3. Or we would say my function 1 over x minus 3 is discontinuous at what number? And that number would be 3. Okay. Whew. All right. E. For n an odd positive integer greater than 1, the odd root, the nth odd root of f of x is continuous wherever the function inside is continuous. So let's say when we say odd positive integer, we're talking about odd roots. So let's make up another function. Let's say f of x equaled the cube root of x plus 1. Well, guess what? For any odd root, pending the function inside, which this class, we're only going to get easy functions on the inside. The domain for any odd root, it doesn't matter if this is the cube root, the 5th root, the 7th root, the 9th root, the 27th root, any odd root, the domain will always be all real numbers, pending a different function inside. Like if this was x plus 1 over x minus 1, then our domain would definitely change. But like I said, we won't get those types of functions in this class, okay? And if we do, well, good. It's going to make you think a little bit. But other than that, keep it simple. All right. And then the last one, for an even positive integer root, the even root of f of x is continuous wherever f of x is continuous and non-negative. So now we're messing with square roots, 4th roots, 6th roots, even roots, the 100th root, as long as it's an even root, right? So let's say I did f of x equal the square root of, we'll just keep it simple, x. This is a square root, and again, it doesn't matter. Square, 4th, 6th, 8th, 10th, 100. The domain for any even root would, you take the inside, and you always set it greater than or equal to 0. That's it. And of course, in interval notation, this would be bracket 0 to infinity. So we would say that this function is continuous from 0 to infinity. Yeah. All right. So those are good examples of domain, which means we have more examples below. All right. So this one says, using continuity properties, which are the ones above, determine where these functions are continuous at. And it is important to know what type of function we're dealing with. So the first function, well, x squared minus 2x plus 1. Guess what type of function this is? This is a polynomial. And from the notes above, the domain of any polynomial is negative infinity to infinity. Oh, that was easy. But I guess we want to say it in continuity type words, so we can say continuous on negative infinity to infinity. That's it. That one was easy. Too easy. Next one. Guess what type of function this one? This one is rational. All right. So which means first let's solve for the domain. And for any type of rational function, you take the denominator and set it equal to 0 and solve for x. Okay, and lucky for us, it's factored already. So if we set this equal to 0 and solve for x, you'll get x equals -2 and x equals 3. But since this is rational, we cannot be equal to these values because they'll make the denominator 0, which will then make the function undefined. So what we say in continuity terms is continuous on -infinity to -2. Oh, running out of room. Hang on, we dropped down one. -infinity to -2 union -2 to 3 union 3 to infinity. And again, we can also say discontinuous at x equals -2 and x equals 3. So however you want to word it. It's better to state the interval notation because we will be using interval notation a lot in this class, especially when we get to graphing using first and second derivatives. Okay, next one. F of x equals the cube root of x squared minus 4. Well, what type of root do we have? We have a cube root function. So we're going to say an odd radical. And if you remember the properties above on your paper, doesn't matter what, well, it matters what's inside, but inside we have a polynomial. So this is an odd radical with a polynomial, which means that by the property above, our domain is going to be all real numbers. Okay. And once again, in our continuity terms, we say this function is continuous on the interval -infinity to infinity. All right, good times. Let's see, very last one. Over here. Looky, looky. We have the square root of x minus 2. So what we have now is an even root function. Even root radical function. Wow, that's a lot of words, right? Okay, so for the domain, take whatever's inside the house and set it greater than or equal to 0. Move that 2 over, and there's our domain. This inequality tells us what interval we are continuous on. So we will say continuous on bracket 2 to infinity. So this function is continuous from 2 to infinity. All right. And there's our lesson in domain and continuity. If you know the domain of a function and you know the type of function, then you know where it is continuous at and where it's discontinuous at. So, perfect. Look at those work hand in hand. All right, next one. Whew, this one is a fun one. And trust me, we're going to create sign charts on this one, which we will also be doing later. We'll be dealing with a lot of sign charts. Okay. So this one says solve inequalities using continuity properties. There's a bunch of foreign stuff up here, so let's get through it. It says, the first theorem says, if f is continuous on some open interval ab and f of x does not equal 0 for all values of x in this open interval, then either f of x is greater than 0 for all values of x in this open interval, or f of x is less than 0 for all values of x in this open interval AB. All right, English. We will create a sign chart that will tell us where the y values are above the x-axis and where the y values are below the x-axis. That's all that theorem says. So that sounded a lot simpler, right? Too bad I didn't write the book. So this says y values above the x-axis. And this one says y values below the x-axis. Okay. And then the next definition says a real number x is a partition number for a function f if f is discontinuous at x or f of x equals 0. So basically this says we're going to solve for the domain of a function and the x-intercepts of a function, and those numbers that we find for x, we will plot on the number line and they will partition it. They will break the number line into pieces. That's all that says. So let's try it out on the problem below. Okay, solve this inequality by constructing a sign chart. Express the solution in inequality notation and interval notation. Okay, awesome. So we are given x plus 1 over x minus 2 greater than 0. So our job is to find x values that will make this function be greater than 0. So what we're really looking at, if you compare it to the theorem I had above, when we finally solve for our x values, what this really wants at the very end is what are the x values that will get us our y values above the x-axis. That's what it wants to know. And in order to figure that out, we need to find the domain and we need to find the x-intercept, make a sign chart, test the sign chart, and then we'll have our answer. Okay, so that's where we're going first. First up is our domain. So we'll say step A, domain. This is a rational function, so take the denominator, set it equal to 0, and solve for x. And of course, we cannot be equal to that because it will make my denominator 0. This is your first partition number. Okay, and then the next part is finding the x-intercept. Okay, well, if you're ever given a rational function, there's a nice little trick to help you solve for x-intercepts. So, two things to know. First thing, on a rational function, domain always comes from the denominator. Second thing, x-intercepts only come from the numerator. With that being said, to find the x-intercepts, just take the numerator and set it equal to 0. All right, one more time. On a rational function, Domain comes from the denominator. X-intercepts come from the numerator. Simple as that. So that's where we're going. So B, find our x-intercept. We take our numerator, x plus 1, set it equal to 0, and solve for x. X equals -1. And we're allowed to be -1 because it came from the numerator. We don't care what goes on in the numerator. The numerator can be whatever numbers they want. The denominator is what we worry about when we mess with domain. Okay. Guess what? You have your second partition number. All right. Step C, number line and plot your partition numbers. Sign charts. And our sign charts should always go from -infinity to +infinity, pending some type of domain from an application problem, but that comes later. Okay, now let's plot our partition numbers. First is x cannot equal 2. So guess what? That's going to make an open circle on my number line at 2. And then x equals -1. We can be -1, so that's going to make a closed circle on my number line or my sign chart. Number line, sign chart, either one. Okay, so after we plot our partition numbers, we now pick test numbers. And when I say test numbers, we're going to pick it between the intervals. My first interval is -infinity to -1. And always think small. I want a number from -infinity to -1. That number is going to be -2. And then my next interval is from -1 to 2. I want a number between -1 and 2. I'm going to pick 0. You can pick 1 as well, or 1.5, or 1.99, as long as it's a number between -1 and 2. And then my last interval, 2 to infinity. Give me a number from 2 to infinity. And we're going to pick 3. Okay, so now we have our test numbers. We will now take these test numbers and plug them in to the original function. And all we care about is the sign of the output. So is it going to be a negative or positive output? Those are going to tell us where the y values are above or below the x-axis, right? Okay. So with that being said, let's show you some cool calculator tricks, right? So let's see. Let me move this here. And let me bring this here. Okay, do that, move myself. Okay, so TI-30, you're gonna do, all right, TI-30 excess or whatnot, you're gonna hit the table button. And then you're gonna type in our function that we're given. So I'm gonna make this into a fraction, and I'm gonna say x plus 1 over x minus 2. After I type it in, I hit enter, 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 make sure it's on ask x, hit enter, enter, and now I'm gonna type in our test numbers we picked down below. -2, 0, and 3. Okay, so we get 1/4, -1/2, and 4. And there you go. That was fast, huh? Way too fast. All right. So then, did I have the graphing calculator one up? I don't. So if you want to see that, I'll show you in class. Okay. I don't want this video to go on for forever. All right. So back here and back there. There we go. All right. So now, look at my test numbers. The first number that came out was positive, which means that for any x value we plug in from -infinity to -1, the y values will always be positive, which means they will be above the x-axis. Now, look at the second value when we plugged in my test number. When we plugged in 0, the y value came out negative. This means that for any number in between -1 and 2, the y values will be negative and below the x-axis. All right. And then one more look. The last y output was a positive 4, which means that from 2 to infinity, no matter what x value I pick, the y values will always be positive and above the x-axis. All right, this is what we're looking for. So actually, let me label some stuff. I'll say above, below, and above. And when I say above and below, I mean above x-axis, below x-axis. Okay, and now all of this work to answer the final question, the question that was asked in the very beginning. I know it's awful. We want to know on what intervals from our sign chart are the y values above the x-axis. That's what we want to know. So look at your sign chart and let's see those intervals. So this is D. We want to know for our rational function, on what intervals are my y values above the x-axis. Now look at the sign chart, and here's our first interval. From -infinity to -1, we are above the x-axis, okay? And then if we look at this interval, this is below. We don't want that. We only want intervals that are above the x-axis. So we skip that and we come to that last interval. This says from 2 to infinity, we are above the x-axis. So we'll say union 2 to infinity. And this is our answer. On these specific intervals, the y values are above the x-axis. So no matter what number you choose between negative infinity and negative 1 and 2 to infinity, the y values will always be above the x-axis. Whew, right? Oh yeah, what did it want? It said, express the inequality, or express the solution in inequality notation and interval notation. Okay. Well, we can have the first one as we want inequality notation, so it's going to be x less than negative 1 and x greater than 2 and x greater than 2. And there it is. There's the inequality representation. Okay. Whew. All right, that was a fun one, right? Lots of mathing. All right, last one. Graph the function, locate all points of discontinuity, and discuss the behavior of f at these points. So, starting, f of x is x squared, so we have a piecewise function. So f of x is x squared, and we can only use x squared if my values of x are less than 1. F of x equals 2x, we can only use 2x if my x values are greater than 1. So, let's go ahead and graph it, and it's going to be easier to find the points of discontinuity once we graph this. So first up, we'll do x squared. I'll say x and y equals x squared. And the restriction to use this one are x values less than 1. So that's where we're starting. I'll put it above there too. X has to be less than 1. So this means we'll start at 1 and go less than. 0, negative 1, negative 2, negative 3. We don't need to go much further. Okay, so now we square out everything and you'll get negative 1, 0, 1, 4, 9. Now remember, I'm taking these values and plugging them into x squared. Okay, but one thing to note here is that can we actually use 1? And the answer is no, because my inequality said, my restriction said, x has to be less than 1. So what that means is that when we graph this, 1, 1 is going to be undefined, which means it'll be an open circle. Okay. Now before we graph that, let's make an XY chart for the next function. So we'll have x and y equals 2x. And for this one, we can only use x values greater than 1. So guess what we're starting with? 1, and we're going bigger than 1. 1, 2, 3, 4, 5. That's all we need. And again, take these numbers, plug them in for x, multiply by 2. 2, 4, 6, 8, 10. And then, once again, can we use 1? And that answer is no, because we have to be greater than 1. So once again, when I grab this point, this will also be undefined. it will be an open circle. So let's get to graphing. Let's see. Okay, we'll graph the blue function first. And make that a little bigger. Okay. So at 1, 1, I have an open circle. Actually, I should make this smaller. 1, 1 will be an open circle. And then 0, 0, negative 1, 1, negative 2, 4, and negative 3, 9. So here's what my first function looks like. There's the blue function from the XY chart. Open circle at 1, 1. Okay. And then the next one, 1, 2, again at 1, and then 2, I'll have an open circle. And then plot. 2, 4, 3, 6, 4, 8, 5, 10. And that's what the next part of my function looks like. Okay, perfect. We have graphed, we made the XY chart, we have our open circles representing, and then the next question says, locate all points of discontinuity. So we must remember what it means to be discontinuous. Does a point exist? Does a limit exist? Does the limit equal a point? Those 3 rules of continuity. Well, just looking at the graph, you can already notice where the discontinuity is. The discontinuity is going to be at x equals 1. Because if you look at the y values at x equals 1, you have an open circle here and an open circle there. So let's just go over that really fast. Let's break down the rules of continuity when x equals 1. So locate all points of discontinuity. So we know at x equals 1, f of x is discontinuous. And we don't even have to prove it by the limit. We can go to rule 2. It fails rule 2. We can say fails rule 2 of continuity. Remember that rule says f of c exists. Well, if I said what is f of 1, look at what happens when you have x at 1. Do we have any point that's defined? We have an open circle, therefore no point is defined, therefore f of 1 would be undefined, which is a fail, which makes f of x discontinuous at x equals 1. Okay. Excellent. So moving on, we have find the y values. So it says find f of x at any point of discontinuity. At any points of discontinuity. This means find the y values at our point of discontinuity. Well, we just said in B that no y values exist. So when x is 1, which is our point of discontinuity, the y values are undefined. So we can say in C, we can say when x is 1, no y values exist, or y values are undefined. Okay. And then very last one. Find the limit as x approaches c of f of x, where c is the point of discontinuity. So what this one wants is, what is the limit as x approaches 1 from both sides of f of x? So we want to know, does a limit exist here? Which means we get to prove more that this function is discontinuous by the rules of discontinuity. So let's look at it. So what we're saying is, as x approaches 1 from the left, what are my y values? Or what is the limit's y value? So as x approaches 1 from the left, we see that this y value gets closer and closer and closer to 1. So the limit from the left is 1. Let me write that down. Actually, yeah, let's make this the limit from the left is 1. And then let's look at the limit from the right at 1. So then, do it again. As you approach 1 from the right, you see that your y values get closer and closer and closer to 2. So the limit from the right is 2. So, quick, run it back. As x approached 1 from the left, y got closer and closer to 1. As x approached 1 from the right, y got closer and closer to 2. So the limit from the left is 1. The limit from the right is 2. Does 1 equal 2? And that answer is no. So we finish this by saying the limit from the right is 2, and therefore these are not equal. So the limit as x approaches 1 from both sides of f of x does not exist. Do not eat. Okay. Therefore, proving further that it is discontinuous at x equals 1, because this would also fail rule 1 of continuity. All right, kids. That is continuity. So, if you know the domain, you know where a function is continuous. If you know the graph, you can see where functions are discontinuous, all that lovely stuff. And that sign chart, evil, but worth it. Okay, that is it for now. See you in the next one.